Hi, chemistry. Just going to create kind of a quick and dirty video here with this University of Colorado PHET solubility demo. I don't know why it and Zoom were conflicting with each other, but I did want to show you this. So we begin with a shaker of just salt, regular old table salt, sodium chloride, and you can see as we put some in, it pretty readily dissolves in water. The red and green, I believe, yeah, over here on the side. Red is supposed to be sodium, green is supposed to be chlorine, and as we shake the cubic crystals of salt into the water, the sodium and the chlorine dissociate into their ions. And with our counts up here in the upper right corner, it's pretty easy to see that all of the sodium and the chlorine particles that we're putting in are dissociating. And salt is extremely soluble in water. There's not a lot that affects its solubility, and you can put a ton of salt, well, not literally a ton, but a lot of salt into water, and it's going to dissolve. So dissociation is just when a polar substance separates an ionic compound into its constituent ions. Let's take a look at a different salt, one that's maybe not quite as soluble, doesn't quite go into water to the extent that sodium chloride does. So we're going to do silver arsenate. So the silver is going to be gray particles. The arsenate polyatomic group is going to be, looks like orange on my screen. So a little different crystal shape. They go in and dissolve. And we see that happen. And at this point, you're probably saying, doesn't look a whole lot different. One thing that is different, however, is that we see differing numbers of particles here, that we have 3 silvers dissolved to every 1 arsenate, and that's because we have a difference in the oxidation states of the silver and the arsenate. And you can probably figure out what the formula of silver arsenate is by looking at the ratios of the particles. One thing we still see, though, is that the bound, meaning particles that have not dissolved, are still right now at 0. So let's do something first. Let's add some more of our silver arsenate salt, and that still dissolves, yay, and we're going to put some more in, and that still dissolves. There was a lot of stuff in there. Let's put some more in, and that still dissolves. Wow, the silver arsenate is really soluble. Uh-oh. Oh no. I think I broke it. We now have this clump of silver arsenate at the bottom that is not dissolved. A lot of particles in solution, and we even see that some particles seem to kind of latch on and then come free of this little clump at the bottom. But if you were actually pouring silver arsenate into a beaker of water in the lab, you'd see that you'd still have little crystals of silver arsenate sitting on the bottom of the beaker and not dissolved. So what's happened here is that we have reached the saturation point. And over in the counts, you'll see that we now have a number of particles that remain bound, meaning not dissolved. And the dissolved represents the limit, or the solubility limit, at this particular amount of water. So it's really governed by how much space there is between the water molecules, the effectiveness of the water molecules to be able to pull the silver and the arsenate apart, the amount of space there for the silver and the arsenate ions to occupy when they're dissolved. So one way that we can make this extra silver arsenate dissolved is we just give it some more room. So if I turn on the faucet and I add water, what we see is that extra silver arsenate now dissolves, and we're good to go. We're now back to 0 on the bound. But if I try to add in more silver arsenate, we can see that now this doesn't dissolve because it's back to saturation, and maybe I can add some more water again. We'll go ahead and fill up the beaker here and see if perhaps we can get it all to dissolve. Sure enough, now it all dissolves. This is going to relate to a concept of concentration. There are also other ways that we could affect the solubility of a substance, and we'll take a look at those. But I thought this visual simulation might help you out in understanding what exactly is going on at the particle level when you dissolve a salt or dissolve any substance into a polar solvent like water.